Earth has spent the last 5 million years drifting through the aftermath of a stellar catastrophe. Not a single explosion, a chain of them. Ancient stars died, one after another, blasting enormous cavities into the fabric of the galaxy and leaving behind a region of space unlike anything the solar system had encountered before. And right now, we are still moving through it. At this moment, Earth is hurtling through the Milky Way at roughly 828,000 kilometers per hour. No wind, no vibration, no sensation of motion at all. Yet every person who has ever lived has been carried along on this journey through a part of the galaxy scientists are still trying to understand. For decades, astronomers assumed the space between stars was mostly empty, but the closer they looked, the stranger it became. The solar system is traveling through a vast structure known as the local bubble, a hollow cavity carved out by long dead stars. Evidence suggests that millions of years ago, conditions beyond our solar system compressed Earth's protective shield and exposed the planet to a harsher galactic environment than it experiences today. The evidence for that event is not theoretical. It is sitting on the ocean floor. Researchers have found traces of radioactive material that could only have arrived from nearby stellar explosions, preserved inside ancient layers of seafloor sediment like fingerprints left behind by the galaxy itself. Then astronomers discovered something else, a strange tunnel like structure extending through our local region of space, a corridor of superheated plasma stretching toward distant constellations, connected to a larger network whose origins remain uncertain. And the deeper scientists investigate our cosmic neighborhood, the more often the models need to be revised. The unsettling realization is that Earth is not traveling through empty space. It is traveling through an environment with a history, a structure, and influences that have already reached our planet before. If space content like this is your thing, we've got plenty more. Subscribe, and you'll have a new documentary waiting for you next time you need one. The story begins with the discovery that the space between the stars is anything but empty. Long before we discovered the structures surrounding our solar system, astronomers began noticing something curious. Starlight arriving from distant regions of the Milky Way was not arriving unchanged. Along its journey, some of it had been absorbed, scattered, and subtly altered by material occupying the vast distances between stars. Space, it turned out, was not empty at all. This material is known as the interstellar medium, often shortened to ISM. In simple terms, it is the matter that fills the galaxy between star systems. Not much matter by earthly standards, but enough to shape the evolution of stars, planets, and entire regions of the Milky Way. The ISM is a diffuse mixture of gas, dust, plasma, and magnetic fields stretching across nearly every corner of our galaxy. Remarkably, it accounts for roughly 15% of the Milky Way's visible mass. Most of this material exists as hydrogen, the simplest and most abundant element in the universe. Some of that hydrogen remains neutral, with its electrons intact. Some exists as plasma, a state of matter in which electrons have been stripped away, leaving charged particles moving freely through space. Mixed among them are molecular clouds, denser regions where atoms combine into molecules. There are also microscopic dust grains, fragments of carbon, silicon, ice, and heavier elements forged inside ancient stars. Threading through everything are magnetic fields, invisible structures that help guide the motion of charged particles across enormous distances. Yet the interstellar medium is anything but uniform. In some places, matter gathers into dense clouds capable of forming new stars. In others, space becomes so thin that only a handful of particles occupy an entire cubic centimeter. Between those extremes lies a constantly changing landscape. Over millions of years, the solar system drifts through these different environments, crossing boundaries we never see and entering regions we cannot detect without instruments. But Earth does not move through this galactic terrain unprotected. Flowing outward from the sun is the solar wind, a continuous stream of charged particles traveling in all directions. Over time, that outflow carves out an enormous cavity in the surrounding interstellar medium. This cavity is called the heliosphere. In plain terms, it is the sun's protective bubble, extending roughly 100 astronomical units from the solar system before meeting the pressure of interstellar space. Every living thing beneath our skies depends on it. The heliosphere acts as a shield, deflecting a large fraction of the energetic particles and radiation arriving from the wider galaxy. Without it, the environment around Earth would be dramatically different. But the heliosphere is not a rigid structure. It breathes, it responds. Its size depends on the conditions beyond its boundary. When the surrounding interstellar medium is hot and thin, the heliosphere expands outward. When the surrounding medium becomes colder and denser, external pressure increases and the bubble contracts. Sometimes the change may be modest, sometimes it may be profound, and that creates a quiet reality beneath everything we have discussed so far. Earth exists inside a protective bubble. It did not build, cannot repair, and does not control, moving steadily through an interstellar environment that never stands still. If we could somehow remove every nearby star from the sky, leaving only the invisible structure surrounding us, our cosmic neighborhood would not look crowded at all. It would look hollow. For roughly the last 5 million years, the solar system has been moving through one of the strangest known regions of the Milky Way. Astronomers call it the local bubble. Despite the name, it is not a neat sphere floating in space. It is a vast cavity carved into the interstellar medium, stretching across approximately 1,000 light years and surrounding our entire solar system. Inside this cavity is plasma, a gas so hot that its atoms have been stripped apart into charged particles. The temperature reaches roughly 1 million degrees Celsius. That sounds violent. Yet the plasma is so thin that it would register as a hard vacuum in any laboratory on Earth. A handful of particles occupy a volume that, by terrestrial standards, would seem almost completely empty. For decades, nobody could see this structure directly. We are inside it, after all. Trying to map it from within is a little like trying to determine the shape of a cave while standing somewhere deep inside its darkness. The breakthrough came through X ray astronomy. Beginning in the late 20th century, observatories detected a faint glow of soft X rays arriving from every direction around the solar system. The signal was subtle but persistent. Soft X rays are a form of high energy light often produced by extremely hot plasma. As more observations accumulated, a picture slowly emerged. The region surrounding our solar system was filled with superheated material, unlike the denser interstellar environments found elsewhere in the galaxy. The glow was not coming from a distant object, it was coming from the space around us. But the local bubble proved difficult to describe with simple geometry. As maps improved, astronomers discovered that the cavity was highly irregular. It bulges in some directions and narrows in others. Some regions extend roughly 300 light years outward, others stretch beyond 600 light years. Rather than resembling a balloon, it looks more like an enormous underground cavern with uneven walls, elongated chambers, and branching corridors reaching into neighboring regions of the galaxy. The structure is also asymmetric. We do not sit at its center. The solar system occupies only one small position within a much larger feature, whose boundaries continue to be refined as new observations arrive. Even today, the exact contours remain a subject of active research. What makes the local bubble remarkable is not simply its size. The Milky Way is filled with large structures. It is the combination of size, temperature, and emptiness that demands explanation. A cavity spanning hundreds of light years does not appear spontaneously. Heating gas to 1 million degrees requires an enormous energy source. Sweeping away surrounding material requires even more. Something excavated this region, something powerful enough to reshape a portion of the galaxy itself. To understand why this cavity exists at all, we have to think in terms of accumulation rather than catastrophe. The local bubble was not created by a single event. It was built gradually, explosion after explosion, over millions of years. Astronomers now believe that the region surrounding us was once filled with ordinary interstellar gas. There was no vast hollow chamber, no million-degree plasma, no enormous cavity stretching across hundreds of light years. The space we now occupy looked much like countless other regions of the Milky Way. Then the stars began to die. A supernova occurs when a massive star reaches the end of its life and can no longer support its own weight. The core collapses. The outer layers are blasted into surrounding space. For a brief period, a single star can outshine an entire galaxy. The energy released is staggering, approximately 10 to the 44th joules. That is enough energy to drive a powerful shock wave through the interstellar medium, sweeping gas and dust outward while heating the interior region into an expanding pocket of thin, hot plasma. One explosion can create a cavity. Several can create something far larger. Current models suggest that between 14 and 20 massive stars exploded within our galactic neighborhood over the last 10 to 15 million years. Each supernova added energy to the growing structure. One shock wave expanded into the wake of another. The cavities merged. The hot interiors combined. Over time, a much larger feature emerged from the collective effects of many stellar deaths rather than a single dramatic event. The most likely source of these explosions is a loose grouping of young massive stars known as the Scorpius-Centaurus OB Association. An OB association is a population of hot, short-lived stars born from the same giant cloud of gas. These stars burn through their fuel quickly. They live fast. They die young. And when enough of them reach the end of their lives within the same region, the surrounding interstellar medium is reshaped on enormous scales. The process has not completely ended. Measurements indicate that the shell surrounding the local bubble is still expanding today at roughly 6.7 kilometers per second. Slowly, almost imperceptibly, the structure continues to evolve. The energy released millions of years ago remains written into the motion of the gas around us. But perhaps the most remarkable discovery arrived in 2022. Using three-dimensional dust mapping and data from the Gaia mission, researchers led by Catherine Zucker reconstructed the local bubble in unprecedented detail. Their work, published in Nature, revealed that nearby star-forming regions are not randomly distributed through space. They sit along the bubble's surface: the Taurus molecular cloud, the Perseus cloud, Ophiuchus, Lupus, Chameleon, and even the region associated with the Pleiades all trace the expanding boundary. As the shell pushed outward, it compressed surrounding gas. Dense pockets formed. Gravity took over. New generations of stars began to emerge. By the time the solar system drifted into this region, approximately 5 million years ago, the local bubble was already ancient, carrying the accumulated legacy of stars that had vanished long before we arrived. Far beneath the waves, where sunlight has never reached and human history occupies only the thinnest layer of time, the seafloor has been keeping a record. Not a written record, not a fossil record, something subtler, a chemical archive, assembled grain by grain over millions of years. As minerals slowly accumulated across parts of the deep ocean, they formed structures known as ferromanganese crusts. These crusts grow extraordinarily slowly, often only a few millimeters every million years. Each new layer captures traces of the environment present when it formed. Over immense spans of time, they become geological tape recorders, preserving events long vanished from the surface world. When scientists began examining these ancient layers in detail, they found something unexpected. They found iron 60. Iron 60 is a radioactive isotope, a rare form of iron containing 26 protons and 34 neutrons. What makes it remarkable is its origin. Unlike ordinary iron, iron 60 is produced almost exclusively during supernova explosions. It is forged in the final violent moments of massive stars and dispersed into space when those stars die. Its radioactive clock is equally important. Iron 60 has a half life of approximately 2.6 million years. That means any iron 60 present when the solar system formed 4.5 billion years ago would have decayed away long ago. If we find iron 60 on Earth today, it cannot be primordial. It must have arrived relatively recently, at least in geological terms. And that is exactly what researchers discovered. Independent studies conducted across multiple ocean basins identified distinct concentrations of iron 60 embedded within ferromanganese crusts and deep sea sediments. The strongest signals appeared in layers corresponding to roughly 2 to 3 million years ago, and again around 6 to 7 million years ago. Different teams, different samples, and different analytical techniques all pointed toward the same conclusion. Material from distant stellar explosions reached Earth. Not metaphorically, physically, atoms forged inside dying stars crossed interstellar space, entered the solar system, drifted through Earth's environment, and settled onto the ocean floor where they remain today. You could hold a sample containing those atoms in a laboratory. The evidence is tangible, but iron 60 is not alone. Researchers have also identified traces of manganese 53 and plutonium 244 within related geological layers. These isotopes serve as additional tracers, chemical fingerprints that help reconstruct periods when Earth experienced enhanced exposure to material arriving from beyond the solar system. Each isotope tells part of the same story. Together, they strengthen the case that our planet encountered debris associated with nearby stellar events. What emerges from this evidence is a different picture of Earth's relationship with the galaxy. We often imagine our world as isolated, protected beneath its atmosphere and magnetic field, yet the ocean floor suggests otherwise. Across millions of years, the boundary between Earth and interstellar space has proven permeable. The stars did not remain distant observers. Their remnants arrived here. The galaxy left signatures in our rocks, our sediments, and the slow mineral layers resting in darkness beneath the sea. 2 million years ago, nothing dramatic happened in the sky above Earth. No brilliant flash announced itself. No nearby star exploded. No obvious marker appeared in the geological record. Yet, according to recent research, our planet may have entered one of the most unusual environmental conditions it has experienced in its recent history. The idea emerged from a 2024 study published in Nature Astronomy by Merav Ofer, Avi Loeb, and their colleagues. Rather than examining the aftermath of ancient supernovae, the team focused on a different possibility. They asked what would happen if the solar system encountered an exceptionally dense cloud of interstellar material while moving through the galaxy. Their models pointed toward a candidate known as the local lynx of cold cloud. This structure is a dense filament of neutral hydrogen located near the edge of the local bubble. Neutral hydrogen simply means hydrogen atoms whose electrons remain attached rather than stripped away. Compared with the hot plasma surrounding much of our local environment, it is colder, denser, and far more resistant to the outward pressure of the solar wind. The contrast is extraordinary. The interior of the local bubble contains roughly 0.005 hydrogen atoms per cubic centimeter. The local lengths of cold cloud contains approximately 3,000 hydrogen atoms per cubic centimeter. The difference is about 600,000-fold. In astronomical terms, that is not a subtle environmental change. It is the equivalent of moving from a nearly empty chamber into a wall of matter. When the heliosphere encounters conditions like these, the balance changes. Normally, the solar wind pushes outward against the surrounding interstellar medium, maintaining the vast protective cavity that surrounds the planets. But if the external pressure rises enough, the solar wind can no longer hold its ground. The boundary contracts inward. The bubble shrinks. According to the simulations, the compression may have been extreme. Today, the heliosphere extends to roughly 100 astronomical units from the sunday. An astronomical unit is the average distance between Earth and the sunday. During the cold cloud encounter, the models suggest the heliosphere may have collapsed to only 0.22 astronomical units. That distance is smaller than the orbit of Mercury and far inside Earth's own path around the sunday. In practical terms, the consequences are difficult to ignore. Earth may have spent time outside the heliosphere entirely. The protective shield generated by the solar wind would no longer have enclosed our planet. Instead, Earth would have moved directly through the interstellar medium itself. That environment carries elevated cosmic ray flux, increased galactic radiation, and a greater influx of interstellar dust and gas. Material that would normally be filtered or deflected could travel much deeper into the inner solar system. What makes the scenario particularly compelling is its timing. The modeled encounter occurred approximately 2 million years ago, remarkably close to the age of the iron 60 signal preserved in deep ocean sediments. The geological archive and the astrophysical models do not prove the same event occurred, but together they describe a moment when the galaxy may have pressed unusually close to Earth. Imagine standing beneath the sky during that distant interval and looking upward. The continents would appear familiar enough. Oceans would still dominate the planet. Winds would still move across the landscape. Yet far above, at the edge of space, the atmosphere may have been behaving in ways unlike anything occurring today. The question is no longer what happened beyond Earth. It is what happened here. In 2024, researchers published a study in Geophysical Research Letters examining how Earth's atmosphere might have responded during the passage through a dense interstellar cloud. Their focus was the mesosphere, a high atmospheric layer extending roughly from 50 to 85 kilometers above the surface. It is a cold, rarefied region where unusual processes can leave subtle but global signatures. The proposed mechanism begins with hydrogen. As the heliosphere contracted, greater quantities of interstellar hydrogen would have entered the inner solar system. Some of those hydrogen atoms eventually reached Earth's upper atmosphere. There, they encountered oxygen already present in the mesosphere. When hydrogen and oxygen combine under suitable conditions, water forms. At those altitudes, water behaves differently. Temperatures in the mesosphere are low enough for tiny ice crystals to develop. According to the models, the increased influx of hydrogen could have substantially increased the formation of these crystals, creating conditions favorable for widespread noctilucent clouds. These are delicate clouds composed of microscopic ice particles suspended near the edge of space and illuminated after sunset. Today, noctilucent clouds are largely restricted to high latitudes. They appear as thin electric blue veils glowing against twilight skies. During the cloud encounter, however, the simulations suggest they may have become far more extensive, spreading well beyond their modern range and altering the appearance of the upper atmosphere across much of the planet. But the changes may not have ended there. The same modeling indicated significant depletion of mesospheric ozone. Ozone is a molecule composed of three oxygen atoms, and it absorbs portions of the sun's ultraviolet radiation before that energy reaches lower atmospheric layers. Reduced ozone concentrations would have allowed increased ultraviolet radiation to penetrate deeper toward the surface. That possibility naturally raises another question. Could the encounter have triggered an ice age? Earlier studies proposed that increased interstellar exposure might have initiated large-scale glaciation. The newer research paints a more restrained picture. The authors concluded that a planet-wide deep freeze appears unlikely based on current evidence, yet they also found that regional climatic disruptions remain plausible. Atmospheric chemistry, radiation balance, and cloud formation could all have shifted in ways that influenced local environments. The timing is intriguing. Approximately 2 million years ago places this event within the Pleistocene, the epoch marked by recurring glacial cycles that would eventually shape the world inhabited by our distant ancestors. Establishing direct connections, however, remains difficult. The crossing may have lasted around 100,000 years. In geological terms, that is a brief episode. In human terms, it is unimaginably long. The models are increasingly sophisticated, but the evidence preserved in rocks and sediments remains incomplete. We can see the outlines of the event. The finer details are still partially hidden within the deep passage of time. At every moment of your life, an invisible frontier surrounds the solar system. It has no surface you could stand on and no color you could see. Yet, it is one of the most consequential structures in our existence. This frontier is the heliosphere. The heliosphere is a vast bubble formed by the solar wind, a continuous stream of charged particles flowing outward from the sun in every direction. These particles travel at speeds ranging from roughly 400 to 800 kilometers per second. They carry the sun's magnetic field with them, pushing outward into surrounding space and creating a protective region that separates our planetary system from the wider galaxy. It is not a perfect sphere. As the solar system moves through the interstellar medium, the heliosphere becomes distorted by the pressure of the environment around it. The result is a shape often compared to a teardrop. The side facing our direction of travel is compressed. The opposite side stretches outward into an extended structure known as the heliotail. The scale is difficult to picture. In the direction facing the galaxy, the heliosphere extends roughly 100 astronomical units from the sunday. An astronomical unit is the average distance between Earth and the sunday. Behind us, the heliotail continues for hundreds of astronomical units more, forming an elongated wake that trails through interstellar space as the solar system advances along its galactic path. Within this structure are several important boundaries. One of them is called the termination shock. This is the region where the solar wind begins to lose its dominance. After racing outward for decades, the particles encounter increasing resistance from the surrounding interstellar medium. Their speed drops below the speed of sound in the local plasma environment. the flow becomes slower and more turbulent. Voyager 1 crossed this boundary in 2004, providing humanity's first direct measurements of this distant frontier. Farther outward lies the heliopause. This is the true edge of the heliosphere. Here, the outward pressure of the solar wind and the inward pressure of the interstellar medium reach equilibrium. Neither side wins. The balance defines the border. In 2012, Voyager 1 crossed the heliopause at approximately 121 astronomical units from the Sun, becoming the first human-made object to enter interstellar space. Beyond that boundary lies the interstellar medium proper, not a distant region, not a separate realm, the actual galactic environment through which the solar system is moving. Every condition we have discussed ultimately originates there, beyond the shield maintained by the Sunday. One of the heliosphere's most important functions is filtering galactic cosmic rays. These are extremely energetic particles, accelerated by supernova explosions, pulsars, and other violent astrophysical processes across the Milky Way. Studies suggest the heliosphere deflects roughly 70% of incoming galactic cosmic rays before they can penetrate deep into the inner solar system. That protection reaches all the way to you. Every forest, ocean, desert, city, and living cell on Earth exists beneath a magnetic bubble powered entirely by our star. Its boundaries lie far beyond the planets, yet its influence shapes conditions throughout the solar system. When that shield changes, the environment beneath it changes as well. On two summer days in 1977, humanity launched two machines that would eventually travel farther than anything we had ever built. At the time, neither spacecraft was intended to explore interstellar space. Their primary targets were the giant planets. Yet, decades later, they became something else entirely. They became our scouts at the edge. Voyager 2 left Earth on August 20th, 1977. Voyager 1 followed on September 5th. Using a rare alignment of the outer planets, both spacecraft gained speed through gravitational assists and continued outward long after their original missions were complete. Year after year, they moved deeper into the distant reaches of the solar system, carrying instruments capable of measuring environments no human being had ever sampled directly. Eventually, they reached the frontier where the sun's influence begins to weaken. Voyager 1 crossed the termination shock in 2004 at a distance of approximately 94 astronomical units. Voyager 2 crossed the same boundary in 2007, but at only 84 astronomical units. The difference was important. If the heliosphere were perfectly symmetrical, both spacecraft would have encountered the boundary at roughly the same distance. They did not. The mismatch revealed that the heliosphere is distorted by conditions beyond itself. External pressure, magnetic fields, and the surrounding interstellar medium shape the bubble unevenly, creating a structure far more complex than early models suggested. But the most significant crossings still lay ahead. In August of 2012, Voyager 1 passed through the heliopause, becoming the first human-made object to enter interstellar space. Voyager 2 followed in November of 2018. For the first time, instruments built on Earth were operating beyond the protective boundary of the heliosphere itself. The transition was unmistakable. Measurements showed a sudden collapse in solar wind particles. At the same time, galactic cosmic rays increased sharply. The spacecraft had moved from a region dominated by the sun into one dominated by the galaxy beyond. Even the magnetic environment changed, revealing that a different set of forces governed the space outside the heliosphere. One result surprised researchers. Models of the local interstellar medium predicted a particular magnetic field orientation near the heliopause. The direction measured by Voyager did not fully match those expectations. The discrepancy suggested that our understanding of the magnetic structure surrounding the solar system was incomplete. The neighborhood beyond the heliosphere was not behaving exactly as anticipated. Another measurement reinforced the importance of the boundary itself. Voyager 1 detected plasma densities in interstellar space roughly 40 times higher than those measured within the heliosphere. Plasma is a gas of charged particles, and the contrast demonstrated that the heliosphere genuinely separates two distinct environments. It is not an abstract boundary, it is a functioning shield. Yet even these historic observations come with limitations. Both Voyagers crossed the heliosphere at only two specific locations. Their measurements are invaluable, but they represent single paths through an immense structure. In many ways, it is like extending a thermometer through a window and attempting to describe an entire planet's atmosphere from one reading. The data transformed our understanding, but the larger landscape remains only partially mapped. If you could step outside the solar system and look back at our position within the local bubble, you would not find us floating near the middle of a vast cavity. We occupy a more offset location, closer to one side than the other, moving through a structure whose boundaries are much nearer than the name alone might suggest. Current reconstructions place the solar system roughly 60 to 90 light years from the geometric center of the local bubble. We reside within the southern half of the cavity, surrounded by hot, diffuse plasma, but not equidistant from its edges. The local bubble is large, yet our location inside it is surprisingly specific. And every cavity has a wall. The boundary of the local bubble marks the place where ancient supernova shockwaves finally exhausted most of their momentum. As those explosions expanded outward, they swept interstellar gas and dust ahead of them. Material accumulated over millions of years, forming a shell surrounding the cavity. Compared with the tenuous interior, this boundary region is substantially denser and colder. It is not smooth. Maps derived from stellar observations and dust surveys reveal a remarkably irregular structure. Some portions of the shell are relatively thick, others appear thinner and more fragmented. In several regions, the boundary is interrupted altogether by interactions with neighboring cavities. The local bubble resembles neither a balloon nor a simple sphere. It is part of a much larger and more complicated landscape. That landscape contains neighbors. Throughout the Milky Way, generations of massive stars have carved similar cavities into the interstellar medium. Astronomers often refer to these larger structures as superbubbles. A superbubble forms when multiple stellar winds and supernova explosions collectively reshape an extended region of space. The local bubble is only one member of a broader network. One neighboring structure is particularly important. Known as the Loop 1 bubble, it occupies an adjacent region of space associated with the Scorpius Centaurus stellar population discussed earlier. Like the local bubble, it was created by massive stars and their eventual explosions. Over time, both cavities expanded toward one another. Eventually, they met. Where the expanding shells collided, they formed a compressed wall of denser interstellar material. This shared boundary remains visible in modern observations and provides further evidence that local space is shaped by interacting structures rather than isolated events. The regions around us are connected, layered, and still evolving. But motion continues. The solar system is not stationary within this environment. As we orbit the Milky Way, our trajectory gradually carries us through different portions of the local bubble. Current models suggest that, Over sufficiently long timescales, we will move closer to denser boundary regions than those surrounding us today. The phrase near future requires patience here. In astronomical terms, it means millions of years rather than decades or centuries. Yet the broader implication remains important. The hot, rarefied interior that currently surrounds the solar system is not a permanent address. We are travelers inside a larger structure, moving through a cavity shaped by ancient stars and drifting toward regions where the character of the interstellar environment will eventually change. In maps of the local galaxy, most structures reveal themselves gradually. A cloud becomes clearer as more observations accumulate. A boundary sharpens as instruments improve. Occasionally, however, a discovery appears that seems to have been hiding in plain sight, waiting for the right technology to uncover it. That happened in 2024. Using observations from the Eros-Sita X-ray telescope, researchers from the Max Planck Institute reported evidence for a remarkable structure extending away from our local region of space. Eros-Sita, launched in 2019, produced the most detailed all-sky survey of soft X-ray emission ever assembled. Within that immense dataset, astronomers identified something unexpected: a tunnel. Not a tunnel in the everyday sense, but a channel of hot, low-density plasma extending outward from the local hot bubble toward the constellation Centaurus. The feature appears as a coherent structure rather than a random fluctuation in the surrounding medium. It occupies real space, it has measurable dimensions, and it does not fit comfortably within the simplest descriptions of our galactic neighborhood. The finding immediately attracted attention. For decades, astrophysicists have predicted that large cavities created by stellar explosions should not remain isolated forever. As superbubbles expand, their boundaries can weaken, overlap, and connect. The result would be a network of passages linking one cavity to another across interstellar distances. Theoretical models suggested such structures should exist. Direct evidence proved harder to find. The newly mapped feature appears to be one of the clearest examples yet observed near the solar system. It resembles a corridor of superheated plasma cutting through denser surrounding material, creating a pathway between regions that might otherwise seem disconnected. Rather than ending abruptly at the local bubble's boundary, local space may continue into a broader, interconnected structure. But important questions remain unanswered. The tunnel points generally toward Centaurus, yet its full extent has not been traced. Researchers cannot currently determine exactly where it leads, how far it stretches, or what other structures it may connect to. The visible portion represents only the section our instruments can presently map with confidence. That uncertainty changes how we think about the interstellar medium itself. The picture emerging from modern observations is not one of smooth gas distributed evenly through the Milky Way. Instead, the galaxy increasingly resembles a vast foam. Cavities created by ancient supernovae overlap with neighboring cavities. Dense walls separate some regions, open channels connect others. Hot plasma occupies certain volumes while colder clouds drift nearby. The structure is layered, dynamic, and deeply irregular. The local bubble is therefore not an isolated chamber. It appears to be one component within a much larger architecture, sculpted by generations of stellar birth and death. The tunnel provides a glimpse of that architecture, revealing that our surroundings extend beyond the boundaries first identified decades ago. For the solar system, the implication is straightforward. The heliosphere responds to the environment around it. Whether our future path carries us toward denser boundary material, interconnected corridors, or other structures not yet fully mapped, the surrounding interstellar conditions will continue shaping the size, form, and behavior of the shield that travels with us through the galaxy. Some discoveries arrive as unexpected objects, others arrive as patterns. A pattern can be even more unsettling because it suggests that something is happening repeatedly while the underlying cause remains hidden. That was the situation in 2009. NASA's Interstellar Boundary Explorer, better known as IBEX, had been launched the previous year with a specific goal. Rather than traveling to the edge of the heliosphere, it would observe that distant boundary remotely. IBEX measured energetic neutral atoms, particles created when charged particles exchange electrons and become electrically neutral. Because they are no longer affected by magnetic fields, these particles travel in straight lines, carrying information from otherwise inaccessible regions near the edge of the heliosphere. The mission's first all-sky maps produced an immediate surprise. Researchers expected a relatively diffuse pattern of emissions spread across the sky. Instead, they found a bright, narrow structure stretching across a vast arc overhead. It appeared almost instantly in the data, standing out so clearly that it could not be ignored. This feature became known simply as the ribbon. The ribbon consists of energetic neutral atoms, arriving preferentially from a specific region surrounding the heliosphere. It is approximately 3 times brighter than the surrounding emission and traces an enormous curve across the sky. Rather than appearing random, it seems linked to the magnetic environment surrounding the solar system. That is where the mystery begins. The ribbon appears to align with a boundary between differing magnetic field orientations in the local interstellar medium. In other words, it may be revealing how the magnetic structure outside the heliosphere interacts with the solar wind flowing outward from the sunday. Yet, despite years of study, the details refuse to settle into a single explanation. Since its discovery, researchers have proposed more than a dozen competing models. Some suggest the ribbon forms just beyond the heliopause. Others place its origin much farther away. Certain theories emphasize particle reflections. Others focus on magnetic trapping mechanisms or secondary charge exchange processes. Each explanation captures part of the observed behavior. None explains everything. The leading hypothesis involves interactions between the solar wind and the local interstellar magnetic field. According to this view, the ribbon emerges where charged particles become organized by magnetic geometry outside the heliosphere before returning as energetic neutral atoms. The challenge is that the required geometry does not perfectly reproduce the shape observed by IBEX. The match is close, but not complete. But science rarely leaves mysteries unattended. In 2025, NASA launched the Interstellar Mapping and Acceleration Probe, known as IMAP. Designed as the successor to IBEX, the mission carries substantially more sensitive instruments capable of observing the heliospheric boundary in far greater detail. Among its objectives is determining whether the ribbon reflects a local magnetic phenomenon, a larger interstellar structure, or something not yet considered. For now, the ribbon remains one of the most intriguing signals in our cosmic neighborhood. It is not located in a distant galaxy or near an exotic black hole. It appears at the boundary of the very shield surrounding our solar system. The fact that we still cannot fully explain it is a reminder that the edge of the heliosphere is not merely a border. It is an active frontier, producing messages from an interstellar environment we have only recently begun to sample directly. If all the gas, dust, and plasma surrounding the solar system suddenly became visible, the local galaxy would still remain incomplete. There is another ingredient woven through every structure we have discussed, one that cannot be seen directly and yet helps determine the shape of nearly everything around us. Magnetic fields. They thread through the interstellar medium from one region of space to another, extending across distances so large that ordinary intuition begins to fail. Unlike the powerful magnets found in laboratories or household devices, interstellar magnetic fields are extraordinarily weak when measured locally. Yet weakness and insignificance are not the same thing. Across hundreds of light years, even a faint magnetic influence can redirect matter, guide charged particles, and reshape entire regions of the galaxy. The local interstellar magnetic field has a strength of approximately 3 microgauss. A microgauss is a unit used to measure magnetic field strength. By comparison, a typical refrigerator magnet is roughly 20,000 times stronger. If you could isolate a tiny patch of the local interstellar field and bring it into your home, you would barely detect it. But space does not operate on household scales. These fields extend through enormous volumes, influencing clouds of gas and plasma that span distances measured in light years. Their effects accumulate slowly. Charged particles do not travel freely through magnetic fields. They bend, spiral, and follow magnetic pathways. Over millions of years, these interactions help shape the distribution of matter throughout the interstellar medium. The result is a galaxy whose structure is influenced not only by gravity and stellar explosions, but also by magnetic architecture stretching invisibly between the stars. That architecture reaches all the way to the heliosphere. The local interstellar magnetic field is not aligned with the solar system's direction of travel. As the heliosphere moves through surrounding space, it encounters magnetic forces arriving from an angle. This misalignment creates a complex interaction near the heliopause, contributing to the asymmetrical shape measured by spacecraft and inferred from observations. One consequence is known as the draping effect. As the heliosphere pushes through the interstellar medium, magnetic field lines become wrapped and compressed around its outer boundary. The process resembles fabric flowing around a moving object, except the fabric consists of invisible magnetic structures extending through space. Outside the heliosphere, these draped field lines create an organized magnetic envelope surrounding the solar system. But when Voyager 1 crossed the heliopause, researchers encountered another surprise. The direction of the local interstellar magnetic field did not fully match prevailing predictions. Instruments detected an orientation different from what many models anticipated. The discrepancy was not enormous, but it was significant enough to reveal gaps in our understanding of the environment beyond the heliosphere. That realization continues to shape modern research. Mapping the local magnetic field has become one of the central goals of heliospheric science. Scientists can estimate densities, temperatures, and particle populations, but accurate predictions require something more. They require knowing the magnetic structure through which the solar system is moving. Without that information, it becomes difficult to forecast how the heliosphere will expand, contract, or change shape as it encounters new regions of the interstellar medium. The invisible architecture matters because everything else responds to it. Every second, particles from distant regions of the galaxy arrive at the edge of the solar system. Most never reach us directly. They encounter magnetic barriers, changing fields, and turbulent regions that alter their paths long before they approach Earth. Yet, some still get through. These travelers are known as galactic cosmic rays. Despite the name, they are not rays in the usual sense. Galactic cosmic rays are high-energy charged particles, primarily protons and atomic nuclei stripped of their electrons. They are launched by some of the most violent events in the universe, including supernova explosions, pulsars, and other extreme astrophysical environments. Accelerated to enormous speeds, many travel through the galaxy for millions of years before encountering the solar system. Their energies span an astonishing range. Some carry millions of electron volts, others carry billions. An electron volt is a unit used to measure the energy of particles at microscopic scales. Most cosmic rays occupy ranges already difficult to imagine. A few exist in a category all their own. In 1991, detectors recorded the most energetic cosmic ray ever observed. Researchers nicknamed it the "Oh my God" particle. Its energy was so immense that a single subatomic particle carried roughly the same kinetic energy as a baseball moving at approximately 90 kilometers per hour. That energy was concentrated into something smaller than an atom. Fortunately, Earth is not fully exposed to this bombardment. The Sun provides a first line of defense. As the solar wind flows outward, it carries the solar magnetic field throughout the heliosphere. Incoming cosmic rays encounter this magnetic environment and are scattered, redirected, or deflected before reaching the inner solar system. Scientists refer to this process as heliospheric modulation. In simple terms, the heliosphere filters part of the cosmic ray population before it can approach Earth. The strength of that filtering changes over time. The Sun follows an approximately 11-year activity cycle. During solar maximum, magnetic activity becomes stronger and more chaotic. Sunspots increase, solar eruptions become more frequent. As a result, cosmic ray flux reaching Earth decreases measurably. During solar minimum, when solar activity weakens, more cosmic rays penetrate inward. The heliosphere expands and contracts in effectiveness, and the difference can be detected by instruments on Earth. But the Sun is not our only shield. Earth possesses its own magnetic field, generated deep within its molten interior. Together, the heliosphere and Earth's magnetosphere form a layered defense system against energetic particles arriving from space. The importance of that second layer became clear approximately 42,000 years ago during the Lashtemp excursion. This event occurred when Earth's magnetic field weakened dramatically during an incomplete geomagnetic reversal attempt. At its weakest point, the field may have fallen to roughly 6% of its current strength. Evidence preserved in ice cores and ancient tree rings indicates that cosmic ray exposure increased substantially across the planet. The lesson is straightforward. Earth exists beneath two protective barriers rather than one. The heliosphere filters incoming particles across the scale of the solar system. Earth's magnetic field provides additional protection closer to home. When either weakens, cosmic ray exposure rises. When both weaken simultaneously, the consequences become far more significant. Astronomers sometimes speak of the solar system's motion as though it were a single journey through a single environment. The reality is far more intricate. Every moment, the sun, the planets, and everything living on Earth are following a path that has already crossed countless regions of the Milky Way, each with its own conditions, densities, and magnetic structures. Reconstructing that journey has become one of the most ambitious mapping projects in modern astronomy. A major contribution comes from the Gaia mission, a European Space Agency observatory designed to measure the positions and motions of stars with extraordinary precision. By tracking the movements of more than 1 billion stars, Gaia allows researchers to work backward through time, reconstructing portions of the solar system's galactic trajectory and the environments through which it has traveled. The scale is immense. The solar system orbits the center of the Milky Way at approximately 828,000 kilometers per hour. At that speed, a complete orbit takes roughly 225 to 250 million years. Astronomers sometimes refer to this interval as a galactic year. Entire mountain ranges can rise and erode during a tiny fraction of a single orbit. Yet tracing the recent path is surprisingly difficult. Knowing the solar system's current velocity is only the beginning. Every nearby star exerts gravitational influence. Molecular clouds contribute their own effects. Stellar associations drift over time. Small uncertainties compound across millions of years. The farther backward researchers attempt to calculate, the more those uncertainties accumulate, gradually widening the range of possible trajectories. Even so, patterns are beginning to emerge. The dense cloud encounter discussed earlier may not have been unique. Several models suggest that approximately 7 million years ago, the solar system passed through or near another region of unusually dense interstellar material. The exact structure remains uncertain, but the possibility is supported by evidence from an entirely different source. The ocean floor, the same geological archives that revealed the younger Iron 60 signal, contain another anomaly. Independent studies have identified a second enrichment of Iron 60 dating to approximately 6 to 7 million years ago. As before, the isotope points toward enhanced exposure to material associated with nearby stellar activity. The timing is consistent with the possibility of another significant encounter between the solar system and a changing interstellar environment. That date places us within the late Miocene epoch. On Earth, this was a world very different from the modern one. Forests, grasslands, and shifting climates were reshaping ecosystems across continents. Somewhere within that era, the first hominins were diverging from the evolutionary lineage that would eventually lead to chimpanzees. It is tempting to draw connections between these biological developments and changing interstellar conditions. But caution matters. At present, no evidence demonstrates that a cloud encounter or increased interstellar exposure directly influenced hominin evolution. The question remains open, unresolved, and scientifically unproven. Researchers continue to investigate the possibility, but conclusions would be premature. What the evidence does reveal is something broader. The solar system has not spent the last 7 million years drifting through a stable, uniform medium. Its recent history includes changing densities, varying conditions, and episodes recorded both in astronomical models and in Earth's own geological archives. The path behind us appears every bit as eventful as the space ahead. A map published in January of 2022 revealed something unexpected about our corner of the Milky Way. Structures that had long been studied as separate objects suddenly appeared connected, not by coincidence, but by a shared origin stretching back millions of years. The study, led by Catherine Zucker and colleagues and published in Nature, used three-dimensional dust mapping to reconstruct the recent history of star formation within roughly 500 light-years of the solar system. By combining precise stellar distances with large-scale measurements of interstellar dust, the researchers created one of the most detailed views ever assembled of our local galactic environment. What emerged was a remarkable pattern. Every major young star-forming region within that volume appeared to occupy the surface of the local bubble. Taurus was there. Ophiuchus was there. Lupus, Chamaeleon, Perseus, and several other stellar nurseries all traced the same expanding structure. Objects previously examined individually now looked like parts of a much larger story. The implication was profound. The local bubble was not simply a cavity left behind by ancient explosions. It had actively participated in creating the next generation of stars. The same structure surrounding the solar system today had spent millions of years reshaping its environment and triggering new stellar birth across a vast region of space. The mechanism is surprisingly elegant. As the local bubble expanded outward, its growing shell swept through the interstellar medium. Gas and dust accumulated along the advancing boundary. Over time, the material became increasingly compressed. Density rose, pressure increased. Eventually, certain regions crossed a critical threshold where gravity began to dominate. At that point, collapse became possible. Clouds that had once drifted through space in diffuse form condensed into dense concentrations of matter. Gravity pulled them inward. Temperatures increased. Protostars emerged. Entire stellar nurseries formed along the expanding edge of the bubble, transforming the aftermath of destruction into sites of creation. The ages of these young stars support that interpretation. Many of the stellar populations associated with these regions are estimated to be between 1 million and 15 million years old. Those ages align closely with the expansion history reconstructed for the local bubble, suggesting that the advancing shell played a direct role in triggering their formation. But this realization changes more than a timeline. The chain of supernovae responsible for shaping our local environment is the same chain that may have periodically altered Earth's exposure to the wider galaxy. The explosions that contributed to heliospheric disturbances and deposited traces of their existence into Earth's geological record also compressed interstellar material into entirely new stars. Creation and disruption emerged from the same process. The stars visible in nearby stellar nurseries are not separate from the story we have been following, they are products of it. Their origins can be traced to the same expanding structures that continue to influence conditions around the solar system today. And the cycle has not ended. Some of these young stars are massive enough to live relatively short lives by stellar standards. Millions of years from now, a fraction of them will exhaust their fuel and explode as supernovae themselves. When that happens, new energy will be injected into the surrounding medium. New cavities may form, existing boundaries may shift. The local bubble, born from ancient stellar deaths, remains part of a process that is still unfolding across our galactic neighborhood. If the local bubble were suddenly removed from every map of the galaxy, the solar system would not be left floating in empty space. It would simply become one small point within a much larger and more intricate environment, a vast interstellar landscape whose structure extends across the Milky Way in every direction. The interstellar medium is not a single substance. It is a layered system composed of regions with dramatically different temperatures, densities, and physical properties. Across the thin galactic disk, cold neutral hydrogen and dense molecular clouds dominate much of the mass. These are the regions where stars are born. Above and below the disk, conditions become more diffuse. Gas grows warmer. Density falls. Between many of the denser structures lies hot ionized material created by generations of stellar activity. Astronomers describe these environments as different phases of the interstellar medium. One phase is the cold neutral medium, with temperatures around 100 Kelvin. Another is the warm neutral medium, typically near 6,000 Kelvin. There is also the warm ionized medium, reaching roughly 10,000 Kelvin. Finally, there is the hot ionized medium, the category that includes the interior of the local bubble, where temperatures approach 1 million Kelvin. The numbers sound extreme, Yet temperature alone does not determine how an environment feels. The hot ionized medium is extraordinarily thin. Its particles are separated by enormous distances compared with any atmosphere on Earth. Even at 1 million degrees, the energy density is so low that a human standing within it would feel essentially nothing. There are simply too few particles available to transfer meaningful heat. But these phases do not remain isolated. Material moves between them through processes operating across millions of years. One of the most important is known as the galactic fountain. When supernova explosions inject energy into the interstellar medium, hot gas can rise above the galactic disk. As it travels outward, it cools. Eventually, it condenses into cooler clouds and begins falling back toward the disk, returning material to regions where future stars may form. The galaxy recycles itself. Gas becomes stars. Stars produce heavier elements. Exploding stars return those elements to space. The interstellar medium absorbs the material and redistributes it through a continuous circulation extending across vast distances and timescales. Within that larger system, the local bubble is only one feature among many. Nearby cavities connect to neighboring cavities. Dense walls separate some regions, while channels link others. Superbubbles overlap. Old supernova remnants merge into larger structures. The result resembles a complex foam of interconnected chambers rather than a uniform ocean of gas. This broader perspective changes how we view the solar system's journey. We are not moving through a smooth background. We are traveling through a structured medium shaped by billions of years of stellar evolution. As the solar system continues its orbit around the Milky Way, it will encounter differing densities, temperatures, and magnetic environments within this galactic foam. Every variation influences the heliosphere to some degree, which is why scientists increasingly focus not only on where we are, but on understanding the changing interstellar landscape through which we move. A journey does not need a destination to have consequences. Sometimes the environment itself changes long before any obvious landmark appears. That is the situation facing the solar system today. We are moving forward through the Milky Way, but the question is not whether we will arrive somewhere dramatic. The question is how the surrounding conditions will gradually evolve along the way. The first point to establish is simple. There is no known imminent catastrophe waiting ahead, no approaching wall of radiation, no confirmed cloud on a collision course with Earth. Current observations do not support such scenarios. Yet the absence of a looming disaster does not mean the environment ahead is uniform. Far from it. The solar system is traveling through a structured interstellar medium shaped by stellar evolution, magnetic fields, and ancient explosions. In our approximate direction of motion lie denser regions associated with the boundaries of the local bubble. There are also known cold neutral clouds distributed throughout the surrounding medium, along with the broader trend toward denser material found within the galactic disk itself. These structures matter. The heliosphere does not exist independently of its surroundings. Its size and shape depend on the pressure exerted by the medium around it. Change the environment, and the heliosphere responds. Current models suggest that over the next few million years, the solar system may approach or interact with denser material near the boundaries of our present cavity. The exact timing remains uncertain. The exact locations are uncertain as well. Small variations in motion and structure become significant across immense timescales. What researchers can say with confidence is that the path ahead is unlikely to remain identical to the environment we occupy now. One useful way to think about this is through the idea of interstellar weather. Weather on Earth emerges from differences in temperature, pressure, and atmospheric circulation. Interstellar weather operates on vastly larger scales, but the principle is similar. As the solar system moves through regions with different densities, temperatures, and magnetic field orientations, the conditions experienced by the heliosphere change. The time scales are longer, the distances are greater, the effects are real. Even relatively modest shifts in the surrounding interstellar medium can alter the heliosphere's dimensions and effectiveness. A slightly denser environment may compress the boundary. A different magnetic orientation may reshape it. Variations in local conditions can influence how effectively cosmic rays are filtered before reaching the inner solar system. This is one reason the IMAP mission is so important. The Interstellar Mapping and Acceleration Probe was designed not only to investigate existing mysteries, but also to establish a detailed baseline of current conditions. Future measurements can then be compared against that baseline, allowing scientists to detect changes in the local interstellar environment as they occur. But honesty remains essential. We know the solar system is moving through a medium that is structured, variable, and dynamic. We know that the heliosphere responds to those changes. What we do not know is exactly which structure lies next along our path, how dense it will be, or precisely when future encounters will occur. The map has become clearer than ever before, yet portions of the road ahead remain uncharted. Not every future encounter involves a vast cavity, a collapsing shield, or the aftermath of exploding stars. Some of the most important transitions may occur at a much smaller scale, within structures so subtle that their boundaries remain difficult to locate even with modern instruments. One such structure is known as the G cloud. Among the nearby features of the local interstellar medium, the G cloud is one of the most specifically identified regions that may lie ahead of the solar system's current path. It is a warm, partially ionized cloud of interstellar gas, distinct from the environment we occupy today. Partially ionized simply means that some atoms have lost electrons while others remain neutral, creating a mixed state between ordinary gas and fully ionized plasma. To understand the G cloud, we first need to know where we are now. The solar system currently resides inside, or very near the trailing edge of, a structure called the local interstellar cloud. This cloud is relatively diffuse and warm, compared with many denser interstellar regions. It spans roughly 30 light years across and surrounds the heliosphere as we travel through the galaxy. Based on present measurements, researchers estimate that the solar system could leave this cloud sometime within the next few thousand to tens of thousands of years. That may sound distant. Astronomically speaking, it is remarkably close. Beyond the local interstellar cloud lies the G cloud. Observations indicate that it sits generally ahead in our direction of travel, making it a plausible candidate for the next distinct interstellar environment the solar system may encounter. The challenge is that the boundary between these two clouds is not sharply defined. Nature rarely draws straight lines through space. Instead, transitions tend to blur. Density changes gradually. Temperatures shift over distance. Ionization levels vary from one region to another. The result is a transition zone whose exact location remains uncertain. Current instruments can identify broad structures, but they cannot yet determine precisely where one cloud ends and the next begins. Even so, the distinction matters. The G cloud appears to possess somewhat different physical properties than our present surroundings. Its density, temperature, and ionization state are not identical to those of the local interstellar cloud. The differences are modest when compared with the dramatic cloud encounters discussed earlier, yet modest does not mean insignificant. The heliosphere is sensitive. Because it exists in balance with the surrounding medium, even relatively small changes in external conditions can alter its dimensions and geometry. A shift in density or pressure may slightly compress the heliosphere. Variations in ionization can influence how particles interact with the solar wind. These effects are measurable, even when they occur gradually. But this is not a dangerous prospect. No evidence suggests that entering the G cloud would threaten Earth or produce catastrophic consequences. What makes the transition important is not danger, but opportunity. It represents a real, observable change in the local interstellar environment, one occurring on timescales that are comparatively near in galactic terms. The solar system is moving through a landscape with discernible structure, and the G cloud may be the next chapter written directly into the space surrounding us. Consider the challenge for a moment. The structures surrounding the solar system span dozens, hundreds, sometimes thousands of light years. Most are invisible, many are too diffuse to detect directly. We cannot send spacecraft across these distances and wait for results. Yet somehow scientists have built maps detailed enough to identify cavities, clouds, tunnels, and magnetic structures throughout our local region of the galaxy. The answer begins with light. Every star produces a spectrum, a spread of colors containing information about the physical processes occurring within it. But starlight rarely arrives untouched. As it travels toward Earth, it passes through interstellar gas. Certain atoms within that gas absorb very specific wavelengths. Those wavelengths disappear from the spectrum, leaving behind characteristic gaps. The missing light becomes evidence. This technique is known as stellar absorption spectroscopy. Spectroscopy simply means analyzing light by separating it into its component wavelengths. By examining which wavelengths have been absorbed, astronomers can determine the composition, density, and distribution of material lying between us and a distant star. Some spectral features are especially useful. Among the most important are the sodium D lines, two yellow wavelengths associated with sodium atoms in interstellar space. These absorption lines serve as valuable tracers of cold neutral hydrogen regions, helping researchers identify structures that would otherwise remain difficult to detect. A star's light becomes a probe extending through the medium between worlds, but gas is only part of the picture. Interstellar dust also leaves measurable signatures. Using observations from missions such as Gaia, astronomers can determine the precise distances to enormous numbers of stars. Gaia measured more than 1 billion stars across the Milky Way. By comparing how much starlight is dimmed and reddened at different distances, researchers can estimate how much dust exists along each line of sight. The result is three-dimensional mapping. Instead of viewing dust as a flat image projected onto the sky, scientists can reconstruct its location throughout space, revealing the density structure of nearby clouds, cavities, and boundaries. Entire regions of the interstellar medium emerge from these measurements, like landscapes, gradually appearing through fog. For hotter structures, another tool becomes essential: the Arosada X-ray telescope, launched in 2019 as a German-Russian mission, produced the most detailed all-sky survey of soft X-ray emission ever assembled. Hot plasma emits X-rays naturally, making Erosida particularly valuable for studying the local bubble and related structures. Its observations helped reveal the interstellar tunnel discussed earlier and transformed our view of the surrounding environment. The scale of the dataset is extraordinary. The survey contains approximately 900,000 X ray sources, providing an unprecedented resource for studying local and distant astrophysical structures. Yet only two human made objects have directly sampled the interstellar medium itself. Voyager 1 and Voyager 2 continue drifting beyond the heliopause, collecting measurements from the immediate environment surrounding the solar system. Every other insight comes from remote observation. We infer temperatures, densities, motions, and compositions by reading signals carried across space. In a very real sense, we are learning about the medium around us the same way an ancient navigator learned about distant shores, by studying subtle clues long before setting foot there. From a distance, it is tempting to imagine the heliosphere as a fixed structure, a permanent shield carried through the galaxy, unchanged from one era to the next. But the boundary surrounding the solar system is not a static object. It is powered by a star, and stars are restless things. The sun supplies everything. Every particle in the solar wind originates there. Every magnetic structure extending through the heliosphere begins there. The shape, strength, and effectiveness of our protective bubble depend not only on the environment beyond it, but also on the activity of the star at its center. That activity follows a rhythm. The sun undergoes an approximately 11-year magnetic cycle, alternating between periods known as solar minimum and solar maximum. During solar minimum, magnetic activity is relatively subdued. Sunspots become less common, large eruptions occur less frequently. During solar maximum, the situation reverses. The sun's magnetic field grows more tangled, more dynamic, and significantly more active. The effects extend far beyond the solar surface. At solar maximum, enhanced magnetic activity strengthens the influence of the solar wind throughout the heliosphere. Incoming cosmic rays encounter a more complex magnetic environment, making it harder for many of them to penetrate toward the inner solar system. Measurements consistently show that cosmic ray flux reaching Earth decreases during these periods. The shield grows stronger, but the process is not perfectly uniform. The solar wind itself changes constantly. Its speed fluctuates, its density varies. The orientation of its embedded magnetic field shifts over time. Some changes occur over days, others unfold across months or years. Together, these variations continuously modify the way energetic particles travel through the heliosphere. The boundary is always adjusting. Among the most dramatic solar events are coronal mass ejections. These eruptions release enormous clouds of plasma and magnetic field into space. A coronal mass ejection can launch billions of tons of solar material outward at extraordinary speeds. As these disturbances propagate through the heliosphere, they temporarily compress portions of the surrounding environment and alter local shielding conditions. The result is a complex magnetic landscape. Different regions of the heliosphere can experience changing levels of protection depending on solar activity, particle flows, and magnetic geometry. The shield is not merely present or absent, it is dynamic. History provides a useful example. Between approximately 1645 and 1715, the sun entered a prolonged period of unusually low activity, known as the Maunder minimum. Sunspots became exceedingly rare. The solar magnetic field weakened compared with typical conditions. During this interval, measurements derived from cosmogenic isotopes indicate that cosmic ray flux reaching Earth increased measurably. The timing is intriguing. The Maunder minimum coincided with the coldest phase of the Little Ice Age in Europe. Some researchers have explored possible connections between reduced solar activity and climatic conditions. Others argue the relationship is more complicated. The debate remains unresolved. What is clear is that the heliosphere responds to influences from two directions at once. The interstellar medium presses inward from outside. The sun powers the shield from within. Neither remains constant. External densities change. Magnetic environments evolve. Solar activity rises and falls through repeating cycles. The heliosphere exists at the intersection of those forces, shaped continuously by conditions beyond it and by the star that sustains it. A particle arrives from deep space, strikes the upper atmosphere, and vanishes. The event lasts less than an instant, yet the consequences continue downward through layers of air, producing cascades of secondary particles that eventually reach the ground beneath our feet. This happens constantly. Cosmic rays are not rare visitors. They are part of Earth's natural environment. At present levels, they contribute only a modest fraction of the background radiation experienced by living organisms. Most of the time, the atmosphere and magnetic field reduce their impact dramatically. Even so, exposure varies with location. People living or working at high altitudes receive more cosmic radiation than those near sea level. Airline pilots and frequent flyers accumulate measurably larger radiation doses over the course of their careers because they spend more time above the thickest layers of atmospheric protection. Life already notices them. One of the most important examples exists in the air itself. When cosmic rays collide with atmospheric atoms, they help produce carbon 14, a radioactive isotope incorporated into living tissues through the carbon cycle. Every tree, animal, and human being contains traces of it. Thousands of years later, scientists can measure the remaining carbon 14 and estimate age through radiocarbon dating. The process depends on cosmic rays. Increase the incoming flux, and carbon 14 production rises. Reduce it, and production falls. Long before we understood the heliosphere or the interstellar medium, biological and geological records were already preserving indirect evidence of changing cosmic ray conditions. But radiation is only part of the discussion. Some researchers have proposed that cosmic rays may influence cloud formation by ionizing molecules in the atmosphere. Ionization simply means stripping electrons from atoms, creating electrically charged particles that can affect chemical interactions. Under this hypothesis, enhanced ionization could encourage the formation of microscopic particles around which water vapor condenses, potentially influencing cloud cover and climate. The idea remains controversial. Experiments and observations have produced mixed results, and no scientific consensus has emerged. The possibility remains under active investigation, illustrating how difficult it can be to trace subtle atmospheric effects through Earth's enormously complex climate system. A more dramatic example comes from approximately 42,000 years ago. During the La Champ excursion, Earth's magnetic field weakened dramatically during an incomplete geomagnetic reversal. Some estimates suggest field strength dropped to roughly 6% of modern values. With less magnetic shielding available, cosmic ray penetration increased substantially. The evidence appears in ice cores, cave deposits, and ancient tree rings distributed around the world. The signal is clear. Its biological consequences are less certain. A 2021 paper published in Science proposed that this interval, sometimes called the Adams event, may have contributed to widespread environmental stress, the decline of megafauna populations, the disappearance of Neanderthals, and significant behavioral changes among early Homo sapiens. The hypothesis remains debated. The elevated cosmic ray exposure is well supported by isotopic evidence. The broader evolutionary consequences are not. Yet the question lingers: if variations in radiation can influence climate, ecosystems, and biological pressures, then the possibility cannot be dismissed outright. Whether interstellar events have ever shaped the course of evolution on Earth remains one of astrobiology's most intriguing unanswered questions, suspended between evidence, uncertainty, and deep time. Look up at the night sky, and it is easy to think of the sun as something special, a star with a unique relationship to its surroundings. Yet the farther astronomy advances, the more we discover that our situation is part of a much larger pattern repeated throughout the Milky Way. The sun is not traveling alone. Every star in the galaxy moves through the interstellar medium. Some drift slowly relative to their surroundings. Others race through space at remarkable speeds. Wherever a star carries a sufficiently strong stellar wind, it creates a protective cavity around itself. Astronomers call this structure an astrosphere, the stellar equivalent of the heliosphere surrounding our own solar system. The principle is the same. A stream of particles flows outward from the star. Interstellar material presses inward. Somewhere between those opposing forces, a boundary forms. That boundary shifts, bends, and responds to changing conditions, creating a local environment unique to that star's journey. We have seen these structures directly. Using infrared and radio telescopes, astronomers have imaged astrospheres around other stars. Some appear as vast bow shocks, curved structures resembling the wake of a ship moving through water. These features form when stellar winds collide with the surrounding interstellar medium, compressing gas and dust into visible arcs that trace the star's motion through space. The galaxy is filled with them. But not all stars shape their surroundings equally. The sun is relatively modest. Massive O-type and B-type stars possess far stronger radiation fields and vastly more powerful stellar winds. These stars inject extraordinary amounts of energy into the interstellar medium throughout their lives. Their influence extends for enormous distances. Over millions of years, the combined winds and radiation from groups of massive stars can excavate superbubbles spanning hundreds or even thousands of light years. Entire regions of the galaxy are sculpted by these processes. Cavities expand, shells collide, dense clouds are compressed, new structures emerge. Nothing remains fixed. Stars form within cold molecular clouds where gravity gathers gas into dense concentrations. As those stars ignite, their light and winds begin reshaping the environment that created them. Eventually, the most massive among them explode as supernovae, blasting heavy elements into surrounding space and generating new cavities within the medium. The debris becomes raw material for future generations of stars. The cycle continues. Across billions of years, the interstellar medium acts less like a static backdrop and more like an evolving ecosystem of matter and energy. Clouds become stars. Stars transform clouds. Stellar deaths create conditions for future births. Every stage influences the next. The scale is almost impossible to absorb. The Milky Way contains an estimated 100 billion stars. Each follows its own path through the galaxy. Each interacts with nearby gas, dust, magnetic fields, and radiation. Each contributes, however slightly, to the continual reshaping of the medium around it. Seen from that perspective, the local bubble becomes something different. It is no longer an isolated curiosity surrounding Earth. It is one expression of a much larger galactic process. The strange structures we have been tracing are not exceptions to the rule, they are the rule itself. The Milky Way is alive with overlapping bubbles, winds, shocks, and transformations, and we are only beginning to learn how to read the patterns they leave behind. Imagine shifting our perspective away from Earth entirely, not to another planet, but to another civilization orbiting another star, somewhere else in the Milky Way. That civilization would face its own atmosphere, its own climate, its own geological history. Yet it would also inherit something less obvious: the interstellar environment surrounding its star. This is where observation begins to blend into speculation. What follows is not established science. It is a question emerging naturally from everything we have discussed so far. If interstellar conditions can influence radiation exposure, alter protective astrospheres, and potentially affect planetary environments, could they also influence the long development of technological civilizations? No one knows, but the possibility is difficult to ignore. Complex life requires time. Technological societies require even more. Evolution must proceed through countless generations. Ecosystems must remain stable enough to support increasing complexity. Civilizations must survive long enough to build knowledge, culture, and technology. What happens if those long intervals are repeatedly interrupted by severe interstellar disturbances? The structure of the galaxy may matter. Astronomers often describe the Milky Way as containing regions with very different environmental conditions. Near the galactic center, stars are packed far more densely together. Supernova rates are higher. Gravitational interactions are more common. Radiation environments can be considerably harsher than those experienced in our own neighborhood. Other regions are quieter. The solar system resides roughly two-thirds of the way from the galactic center toward the outer edge of the disk. We occupy a relatively calm interarm region between major spiral structures. Stellar densities are lower. Catastrophic nearby events are less frequent. The surrounding interstellar environment appears comparatively stable across long timescales. That circumstance may not be universal. A planetary system embedded deep within dense spiral arm material could experience a more turbulent history. Its astrosphere might encounter changing interstellar conditions more frequently. Nearby stellar explosions could occur at shorter intervals. The long continuity needed for biological and technological development might become harder to maintain. This idea connects to a broader concept known as the galactic habitable zone. The galactic habitable zone is the hypothesis that certain regions of the Milky Way provide a more favorable balance of conditions for complex life. Too close to the center, and radiation hazards increase. Too far outward, and heavy elements needed for rocky planets become less abundant. Somewhere between those extremes may lie a range where life has its best chance to flourish. Earth falls within most proposed versions of that zone. Some researchers have wondered whether our location inside the local bubble adds another layer of protection. The low-density environment surrounding the solar system may have reduced certain hazards while preserving the stability of the heliosphere across long periods. If so, habitability may depend not only on a planet and its star, but also on the larger interstellar neighborhood. But we should be careful. These ideas remain frameworks for thinking rather than conclusions. We do not know whether interstellar environments act as filters on civilization. We do not know whether calmer regions truly produce more technological species. What we do know is that life does not develop in isolation. Every world is embedded within a larger galactic setting, and that setting may shape far more of its story than we currently understand. Some scientific fields advance slowly, accumulating small pieces of evidence across generations. Others enter periods when new instruments arrive all at once, transforming decades of uncertainty into active discovery. The study of our local interstellar environment is now living through one of those moments. The tools are already operating. At the center of this effort is the Interstellar Mapping and Acceleration Probe, better known as IMAP. Launched in 2025, the spacecraft occupies the Lagrange 1 point, a gravitational balance location between Earth and the Sunday. From there, it continuously monitors the interaction between the heliosphere and the surrounding interstellar medium. Its capabilities are extraordinary. IMAP carries 10 scientific instruments specifically designed to study energetic particles, magnetic fields, and the structure of the heliospheric boundary. For several key measurements, its sensitivity is approximately 100 times greater than that of its predecessor, IBEX. Questions that have persisted for more than a decade, including the true nature of the ribbon and the detailed geometry of the heliosphere, may finally receive clearer answers. The mission is designed for precision. Every incoming particle carries information about the environment beyond the solar system. By collecting vastly larger datasets than previous missions, IMAP aims to construct a far more detailed picture of the region through which Earth is currently traveling. But new spacecraft are not the only source of information. Far beyond the planets, two aging explorers continue their journey. Voyager 1 and Voyager 2 remain operational despite approaching half a century in space. Their electrical power is slowly declining, and mission teams must carefully manage which instruments remain active. Even so, both spacecraft continue transmitting data from beyond the heliopause. They are still moving outward. Each year, the Voyagers travel approximately 3.6 astronomical units farther into interstellar space. No other human-made objects have reached this environment. Every measurement they return represents a direct sample of conditions beyond the sun's protective bubble. Meanwhile, observations from Earth are expanding rapidly. The 4-meter multi-object spectroscopic telescope survey, known as 4MOST, is collecting enormous quantities of stellar data that help map the distribution of gas and dust throughout the galaxy. The upcoming Vera Rubin Observatory will add unprecedented depth and resolution, allowing astronomers to trace interstellar structures with far greater detail than previously possible. Unexpected connections are emerging as well. Projects such as Nanograv monitor pulsars, rapidly rotating neutron stars that function as extraordinarily precise cosmic clocks. Tiny changes in pulsar timing are used to search for gravitational waves. Yet those signals must first pass through the interstellar medium. Variations in electron density can alter the timing measurements, linking the study of gravitational waves directly to the study of interstellar structure. Different fields now overlap. The result is a remarkable acceleration of knowledge. In only the last 5 years, our understanding of the local interstellar environment has changed dramatically. The cold cloud encounter models, the discovery of the interstellar tunnel, advances in heliospheric mapping, and new measurements of magnetic structure all emerged from a field moving faster than at any previous point in its history. We are no longer simply describing the region around us. For the first time, we are beginning to watch it unfold in real time. A completed map often creates the illusion that a journey is finished. Lines are drawn, structures are named, distances are measured. Yet in science, the most revealing maps frequently highlight what remains blank. The closer we examine our interstellar surroundings, the more clearly we see the boundaries of current knowledge. Some uncertainties are surprisingly fundamental. We know the solar system is moving through the galaxy. We can measure its present velocity with remarkable precision. We can reconstruct portions of its past trajectory. Yet predicting its exact path through the interstellar medium over the next million years remains extraordinarily difficult. Every nearby star exerts gravity. Every molecular cloud contributes influence. Tiny uncertainties accumulate over immense timescales until precise forecasts become unreliable. The future becomes statistical. Questions also remain about the G cloud. We know it exists. We know it lies near the solar system's direction of travel. We know it differs from our current local environment. But its precise density, magnetic structure, and internal composition remain incompletely constrained. Because of that, scientists cannot yet determine exactly how the heliosphere will respond when the transition eventually occurs. Another mystery points outward. The interstellar tunnel, identified through recent X ray observations, appears to be a genuine physical structure. Its orientation can be measured. Its existence is supported by data. Yet its origin remains uncertain. Its full extent has not been mapped. We do not know where it ultimately leads, nor how it connects to larger structures within the surrounding medium. Closer to home, the ribbon remains unresolved. More than 15 years after its discovery, no explanation has achieved universal acceptance. Competing models continue to reproduce some features while struggling with others. The phenomenon remains one of the clearest reminders that the boundary of our own heliosphere still contains surprises. The geological record raises further questions. Evidence suggests significant interstellar encounters occurred approximately 2 million and 7 million years ago. The physical signatures are persuasive, the biological consequences are not. Did elevated radiation alter ecosystems? Did changing atmospheric conditions influence evolutionary pressures? Or were the effects too subtle to leave a clear biological trace? Current evidence cannot provide definitive answers. There may be additional encounters hidden in Earth's history as well. Ocean sediments, ice records, and isotopic archives continue to be examined for signs of past interactions with dense interstellar clouds. It remains possible that other crossings occurred, but have not yet been identified or correctly interpreted. Climate introduces another layer of uncertainty. Researchers continue investigating whether long-term variations in cosmic ray flux influence atmospheric processes strongly enough to affect climate over geological timescales. Evidence exists, counterarguments exist as well. The magnitude of any effect remains actively debated. None of these unanswered questions represent failure. They mark the frontier. Science advances by identifying where explanations end and investigation begins. Every uncertainty described here has active researchers studying it. Observatories collect new data. Spacecraft transmit new measurements. Papers are published. Models are revised. The edges of ignorance are constantly being redrawn. That may be the most important point of all. The unknown region surrounding these questions is not shrinking because certainty has arrived. It is shrinking because we now know precisely where to look next. Long before the first oceans formed on Earth, before continents assembled and broke apart, before a single living cell left a trace in stone, the solar system had already begun a journey through a galaxy that was itself changing. Every atom in your body has traveled that route with it, carried across distances so vast that ordinary measures become almost meaningless. The numbers are difficult to hold in the mind. Over approximately 4.5 billion years, the solar system has completed somewhere between 18 and 20 full revolutions around the center of the Milky Way. Each galactic year lasts roughly 225 to 250 million years. During every orbit, the Sun and its planets move through regions shaped by different stellar populations, different gas densities, different magnetic environments, and different histories of stellar birth and death. The galaxy is not uniform. Its spiral structure contains concentrations of stars, molecular clouds, and interstellar material that vary dramatically from place to place. As the solar system circles the galactic center at roughly 828,000 kilometers per hour, it repeatedly encounters changing surroundings. Some regions are comparatively sparse, others contain far greater concentrations of gas, dust, and massive stars. The journey also moves vertically. The solar system does not travel in a perfectly flat circle confined to the galactic disk. Instead, it oscillates above and below the plane of the Milky Way in a slow, rhythmic motion. One full vertical cycle takes roughly 60 million years, carrying the solar system through the denser regions of the disk approximately every 30 million years. This motion changes the environment around us. Near the galactic plane, interstellar material becomes more abundant, stellar densities increase, molecular clouds become more common. Farther from the plane, conditions grow somewhat less crowded. Over geological timescales, Earth repeatedly experiences both settings as part of its normal galactic orbit. Some researchers have wondered whether these crossings leave detectable marks. Among the most discussed ideas is the Rampino-Stuthers hypothesis. In its broadest form, the proposal suggests that periodic passages through denser regions of the galactic plane may disturb distant reservoirs of icy bodies surrounding the solar system. This reservoir, known as the Oort cloud, is a vast population of cometary objects extending far beyond the planets. If gravitational disturbances increased the number of comets entering the inner solar system, impact rates on Earth might rise as well. It is an intriguing possibility, but it remains controversial. Statistical analyses have produced conflicting results. Some studies report patterns that appear suggestive, others find little evidence for a consistent relationship. At present, no scientific consensus supports a direct connection between galactic plane crossings and mass extinction events. Yet the broader perspective remains remarkably clear. Earth has already survived 4.5 billion years of galactic travel. It has crossed changing magnetic fields, evolving spiral structures, shifting interstellar environments, and countless regions long erased from direct memory. The history of life has unfolded beneath those changing skies. Our planet's story has never been separate from the Milky Way. It has always been carried within it, orbit after orbit, through a galaxy that has been transforming for the entire duration of Earth's existence. For most of human history, the ground beneath your feet appeared to be the whole story. Mountains marked horizons. Oceans defined limits. The sky seemed distant but fixed, a backdrop rather than a place. Even after telescopes revealed other worlds, Earth still felt enclosed within a comprehensible stage, yet everything we have explored on this journey suggests something far stranger. You are standing on a planet, orbiting a star, inside a magnetic bubble, suspended within a cavity of superheated plasma, all moving through a galaxy at nearly 1 million kilometers per hour. And none of it is visible. The local bubble cannot be seen with unaided eyes. The heliosphere leaves no outline across the sky. Interstellar clouds drift around us without color or shape. Magnetic fields stretch across hundreds of light years without casting a shadow. Entire structures that influence the conditions of life on Earth remained completely unknown until the 20th century, not because they were distant, but because they occupied scales and forms beyond ordinary perception. We learned of them indirectly: a missing wavelength in starlight, a faint glow in X rays, a spacecraft crossing an invisible boundary billions of kilometers away. Piece by piece, a hidden environment emerged, not through a single discovery, but through decades of careful observation. The region surrounding Earth turned out to be far larger, more dynamic, and more interconnected than anyone had imagined. Look upward tonight. Some of the light entering your eyes began its journey long before any scientist knew what the heliosphere was. Some photons left their stars before the local bubble had a name. A few may have departed before human civilization existed at all. While that light crossed the galaxy, generations lived and vanished beneath changing skies, unaware of the structures silently shaping their cosmic surroundings. The scale becomes difficult to grasp. The protections that help make Earth habitable are not walls or shields in any familiar sense. They are enormous astrophysical systems, operating across distances measured in astronomical units and light years. They evolve over thousands, millions, and sometimes tens of millions of years. Compared to those timescales, all of recorded history occupies only the thinnest fraction of a moment. But those vast processes are not separate from us. Approximately 2 million years ago, during the encounter we explored earlier, the heliosphere may have contracted dramatically. Interstellar material likely penetrated deep into the solar system. Cosmic ray exposure increased. Conditions changed in ways still being investigated. Yet on Earth, early human ancestors continued their lives across the landscapes of East Africa. They noticed nothing unusual. No warning appeared in the sky. No visible frontier marked the crossing. The galaxy altered the environment around them without announcing itself. Life continued, generation after generation, beneath forces operating far beyond immediate awareness, and perhaps that is one of the most remarkable realizations of all. The universe does not need to be seen to shape our story. Much of what protects us, surrounds us, and influences us exists entirely beyond the limits of human senses, waiting patiently to be discovered. There is a curious pattern in the history of discovery. Each time we think we have reached the edge of understanding, the boundary moves. New instruments arrive, new data appears. Familiar maps become incomplete. The universe does not become smaller, it becomes deeper. Even after everything we have explored about our local galactic environment, some of the most important structures remain only partially understood. The ibex ribbon is one example. For more than 15 years, scientists have studied this bright arc of energetic neutral atoms wrapped across the sky near the boundary of the heliosphere. It was not a subtle signal buried in noise. It appeared immediately in the first all sky maps. It was obvious, unexpected, persistent. Since then, more than a dozen explanations have been proposed. Some fit parts of the data, others explain different details. Yet no single model has achieved universal acceptance. And this is happening in our own neighborhood, not across another galaxy, not around a distant star. The ribbon exists at the edge of the bubble that surrounds the solar system itself. We live inside a structure that continues to resist complete explanation. In a sense, we always have. The difference is that modern science allows us to identify the mystery with extraordinary precision. That may be one of humanity's most remarkable achievements. Every civilization that ever existed looked upward and encountered the unknown. Ancient observers watched the same stars that shine overhead today. They noticed patterns, they told stories, they searched for meaning. What separates us from them is not the presence of mystery, it is the growing ability to measure it, map it, and define its contours. Yet even now, the unknown remains close. Consider the interstellar tunnel revealed through recent observations. Somewhere beyond the local bubble lies a corridor of hot plasma extending toward the constellation Centaurus. Its existence appears real. Its structure has been mapped, but its full extent remains uncertain. Its destination is unknown. It may have persisted for millions of years while Earth completed countless revolutions around the Sunday. We became aware of it only recently. That realization carries a particular kind of perspective, not fear, not unease, something quieter, the recognition that reality contains layers still waiting to be uncovered. The closer we examine our surroundings, the more intricate they appear. Every answer exposes additional questions. Every boundary reveals another landscape beyond it. Perhaps that is part of the experience of looking into the night sky. You may be lying in darkness while the planet turns beneath you. The Earth continues its orbit around the Sunday. The Sun continues its passage through the galaxy. Around all of it stretches an environment shaped by magnetic fields, interstellar clouds, ancient supernovae, and structures that cannot be seen directly. Some are understood, others remain uncertain. But there is a strange comfort in that awareness. You are not isolated beneath an empty sky. You are traveling through a universe still rich with unanswered questions, accompanied by billions of others who have shared the same curiosity, the same wonder, and the same quiet recognition that the unknown is not a void, it is a place where discovery continues. If we follow the story all the way back, beyond planets, beyond oceans, beyond the birth of the sun itself, we eventually arrive at stars that lived and died before our solar system existed. The iron carried through your blood was forged inside those ancient furnaces. It was scattered across space by explosions powerful enough to reshape entire regions of the galaxy. Some of that material may have traveled through the same chain of supernova remnants that helped carve the cavity surrounding us today. The forces that built the local bubble, altered the heliosphere, seeded future generations of stars, and left faint signatures on the ocean floor are not separate stories. They are parts of one continuous process stretching across millions of years. And the journey continues. The solar system is still moving. It has never paused. While continents shift slowly beneath us and civilizations rise and fade, our star carries its family of worlds through the interstellar medium. In time, we will pass beyond our current surroundings. We will encounter the G cloud. We will draw closer to denser regions near the boundary of the local bubble. Far beyond that lie environments no telescope has yet mapped in detail, and no spacecraft has directly sampled. Those future regions already exist. Somewhere within the expanding shell structures around us, dense pockets of gas continue their slow collapse under gravity. Within those clouds are stars that have not yet ignited. 10 million years from now, entirely new suns may shine in the night sky of whatever life exists on Earth. Their origins are taking shape even now, hidden within material, compressed by events that began long before humans appeared. But this has never been a story about prediction. It has been a story about perspective. Scientists say Earth is entering a strange part of space they cannot fully explain. In one sense, that statement is absolutely true. Yet, every generation could have said something similar. Every region of space the solar system has crossed was once unfamiliar. Every boundary we have reached has revealed structures, processes, and relationships that were previously unknown. The strangeness is not temporary. The not knowing is not a flaw waiting to be corrected. It is the natural condition of existing within a universe larger than any model we create. With each new instrument, the map expands. With each expansion, new questions appear. Knowledge grows, but so does the visible horizon of mystery surrounding it. And so, we arrive at the present moment, somewhere beyond the heliopause, beyond the protective bubble that surrounds our world. Two spacecraft launched in the 1970s continue their silent voyage through interstellar space. Their instruments still gather information. Their transmitters still send signals home. The messages travel at the speed of light, yet they require more than 22 hours to reach Earth. That distance is humbling. Tonight, the edge of direct human exploration sits more than 22 light hours away, drifting through darkness between the stars. Beyond it stretches a vast interstellar landscape, still only partially understood. And there, in that quiet expanse, is where the frontier of our knowledge rests, moving onward through the dark, one signal at a time.